Hi everyone, welcome to the PTAP tutorial sessions. Before we get started, I'd like to give you a short summary of this 10 minutes video. This video explains our team's framework for time series data and implementation of the core parts using Python. The focus is at this GitHub. Okay, let's look at how PTAP works. PTAP, which stands for Prototypes of Temporally Activated Patterns, is our new framework to extract and analyze sequential representations captured by a temporal neural network. Given a temporal neural network, PTAP extracts input subsequences that attribute high activation values. Then we select and visualize representative patterns from extracted subsequences using a new prototype selection method. As a result, the outputs of PTAP are representative patterns that activate the internal nodes the most. Theoretically, if internal operation from a temporal convolutional neural network can be input into PTAP, it will be able to work using any deep learning framework such as TensorFlow, Keras, or PyTorch. Our original code has been implemented using TensorFlow version 1, but I made this tutorial using Keras. To run this code, first, we need to download a univariate dataset in your working directory. I strongly recommended you use dataset from the UCR repository. Also, here a sample dataset stylized corpus is uploaded. Today, I will run my code on Google Colab. So I already downloaded dataset on my Google Drive. Okay, click this button to run code on Colab. I will skip to explain how to data load and train model. And then let's start from here. TAP is define the temporally activated patterns, which means highly activated subsequences. To extract highly activated subsequences, we need to define subsequences and set the threshold for high activation. In this framework, subsequences mean receptive field in convolutional neural networks. In this part, we calculate the length of receptive field and indexes. Besides, we assume that the higher value in neural network is, the stronger its effect on model's decision. This is because as the neural network is trained, the values are also updated according to the training of the neural network, and the result is much improved model performance. Here, the model's internal operation is loaded. I set layer name as pool3, so max pooling of layer 3 is loaded. Then, top 5% value is set to the threshold using NumPy percentile module. Then, all output values are converted to true or false depending on threshold. Then, if An output is true, I mean it's not zero. That values is stored in this array. Finally, receptive field of top 5 becomes pattern. Also, some other information like pattern index, data index, or features, and so on are stored for prototype selections and visualizations. These are output patterns. As you can see, these patterns can look similar or quite different. I mean, these two patterns have a small hill, and these patterns rise gradually. So if there are appropriate prototypes, we can categorize each pattern according to prototypes. To understand more clearly, I show another output. Here, the prototype false shape has a hill, then corresponding patterns also have hills. So, how can the model choose good examples from a lot of temporally activated patterns? Again, the goal here is to find a set of prototypes that reflects the entire sample. There are several ways to select prototypes for clustering. In this model, a greedy algorithm is used with maximum mean discrepancy, which is a distance metric that evaluates the expected maximum difference between two distributions. In the process of calculating distances among patterns, the model can obtain high-quality prototypes in which the intra-class similarity is high and the inter-class similarity is low. For more theoretical detail, refer to our paper, but for now, I will simply explain how our code works. The objective of the select greedy protos is define prototypes. Here, vector 3 is the difference between two objective functions, vector 1 and vector 2, and maximum index becomes the maximum of vector 3. And this function has two parameters. K is a corner matrix and M is the number of prototypes. And it returns a list of selected prototypes and the list of objective functions. About corner, an arbitrary use input values is often chosen for MMD. However, the gram matrix with feature values is used here to improve performance. The result depicts prototypes from our method that reflect various temporal patterns. Okay, I have briefly explained the core parts of our code. From here, I will explain the overall process again. First, it loads datasets and trains state models. Second, it extracts patterns from a temporal neural network's output. Third, it produces a gram corner using the model's features. Fourth, it calls select greedy photo and set parameters K as gram corner and M as 8. It's possible to change the values to whatever you want here. And 50 visualizes and checks the prototypes. As shown below, it produces 8 prototypes because we set the parameter M to 8. finally, present visualization of prototypes with their original input subsequences. Actually, patterns are easily overlapped. We choose some of them randomly. In the resulting graphical image, the black line represents the input subsequences. The colored lines are the prototypes, and the shaded lines are the prototypes variations. And this is end of this tutorial. And if you want more details, please contact us. Thank you for listening.